Hi, good afternoon, everyone. So this week we are studying geometry. For this 30-week program, this is the very first week, I believe, that we are talking about geometry. For many students, they feel that geometry is the most difficult subject across the multiple subjects, in particular the four subjects, typically competition math, middle school, high school competition math would require them to do. But actually, geometry perhaps is the just most interesting and most exciting subjects, and it's not necessarily the most difficult at all. One of the reasons many students feel geometry is difficult is because, to be perfectly honest with you, in this country, in America, schools do not seriously teach geometry in the first place. And that is actually reflected in all the geometry problems you actually see before you reach any, say, JMO or AMO level of geometry. Until then, you won't have any proof type geometry problem in any competition math. So that actually significantly limited what kind of geometry you can learn and what kind of geometry problems you can work on. Unless and until you actually do some proof-based geometry problems, you're not actually studying real geometry. All the problems in those AMC, Mathcounts, or AIME geometry problem, they're kind of combination of a geometry, typically with algebra. Sometimes could be other just subjects, even like a number theory. So don't be too afraid of geometry, because seriously, you have not even seen the real geometry problems, which are even more challenging, but even more interesting. It's hard to instill that thought into your mind because you don't know what I'm talking about unless you do serious geometry by doing a lot of proofs. And that's actually the essence of studying geometry. It's a wonderful tool to train your reasoning and logical just development capabilities so that you learn how to do just mathematical thinking and how to write a rigorous proof. Unfortunately, in the problem that you will do in the next several years, you don't have that type of opportunities. So, and also because the geometry you typically learn in school does not give you that type of just a reasoning and a proof writing type of training, the geometry you actually studied is not complete. That perhaps caused some of the perceived difficulty that you guys from time to time feel about. I don't have any just recommended cure for that unless you want to really spend time to study some serious geometry. Other than that, it's more about doing some problems and sharpen your skills outside geometry, typically algebra. So when that happens, you will find that you will become a better problem solver for those so-called geometry problems. But you do need to develop some very good sense or feelings about geometry. So we will talk about that today to see what that means. It's very similar to a number sense capability when you work on some number crunching problems. You need to have a very good, very intimate feeling about geometry figures. Okay, So let's do a very quick review of some of the most important things about triangles. Everybody should be super familiar with the Pythagoras Theorem, where you have a right triangle. It has three sides, A and B, just the two legs adjacent to the right angle. And the longer side, what we call hypotenuse, is C here. So the Pythagoras Theorem says that C squared equals to A squared plus B squared. So the square of the hypotenuse is the sum of the squares of the other two sides, which are the legs. Of course, based on this equation, you can derive A and B and C from the other two sides in the formula like this. Pythagoras Theorem is such an important theorem that I think it's ranked in about top 10 mathematical theorems or results of all time. And its meaning extends far beyond geometry. It has many profound implications in nearly all other branches of mathematics, which you will see in the future if you pursue just a more advanced mathematical study. But for elementary or Euclidean geometry, which we are studying, this theorem also can find many very interesting applications. There's a website, I think it's called cutknots.com, something, where you can find over 100 different proofs of the Pythagoras Theorem. Even one of the United States president, I don't remember his name, but there was a president who provided individually discovered the proof for the Pythagoras Theorem. So very interesting website. If you have time, go find that website and take a look. Okay, that's Pythagoras Theorem. So a lot of times, especially for middle schools, geometry involves a lot of triangle-related problems, and everybody should be very familiar with three types of special triangles. And the one listed here is the 30, 60, 90 triangle, which is deserves some quick review. When we have a 30, 60, 90 triangle, the sides have a very specific ratio, that is 1 square root of 3 and 2. And because this is a general property that if you take the midpoint of the hypotenuse and connect that with the vertex of the right angle, then you can prove that this one half of the hypotenuse is congruent to this midline from the vertex of the right angle to the midpoint of the hypotenuse. This is generally true for any right triangles. But because this is 30, 60, 90 triangle, we also see that because this angle is 60 degree, then this must be also 60 degree because this side is congruent to this side. So it turns out that for this 30, 60, 90 triangle, we also have such an equilateral triangle right there. That's why this triangle is so special. So the three sides is in the ratio 1 to the square root of 3 and to 2. And it has many very interesting properties. So another special triangle is, of course, the 45, 45 right triangle, where you have isosceles right triangle. So this one is much simpler because now if you get the sides, the two congruent sides is 1, then the hypotenuse is easily square root of 2. And of course, you have the two base angles at 45 degree. And the third interesting or special triangle is, of course, the equilateral triangle. where you have all the sides congruent to each other. So each angle is 60 degrees. And because if you take a, say, this important symmetrical line, which can be considered as the either the angle bisector or the midline, or this is the perpendicular line, which is also the altitude, you will see that 1/2 of the equilateral triangle is just this special 30, 60, 90 triangle. So therefore, easily, if you have side length is 1, then this height or altitude, whatever you call it, or midline, must be square root of 3 over 2 because of this ratio. See, this is the longer side of the 30, 60, 90 triangle. So you do need to memorize the area formula for this one just to make it more available, make that result more available. So what is the area of such a equilateral triangle? You can easily see that it must be this one, because now the altitude is this one and the base is this one. So if this is 1/2, then you have to times 1 times this one, then divided by 2, where you get this area formula. So of course, if the length is a instead of 1, then easily the area of this equilateral triangle will be a squared over this one. You just simply scale it up. And this is a property of a proportional reasoning. Okay, so that's a very quick review of some special triangles that you really need to be very familiar with, because during competition math, you just don't have any time to derive those results on the fly. You really need to memorize that. Okay, so now let's take a look at today's first problem. So we have this a figure where you have a triangle ABC. This is 3, and this is 4, and this angle is 120. Then you draw perpendicular from those 2 points to meet at a certain point. So we label that as A, B, C, D in this order. So A, B, C, D. And now the question is, what is the length of CD? Okay. So as I earlier mentioned, you want to develop really some good sense about geometry, which is very similar to number sense for numbers. So for this type of problem, when you see 120 degree, what is the first thing coming to your mind? It should be, this is a special angle. Why? Because its supplement is 60 degree, right? If you take a look at this, this must be 60 degree. And we know 60 degree, especially when you are already told that you have two right angles, this should give you some just intuitive thinking. You want to build or find some special triangles. Another point is that you should be very familiar with the formula for the sum of all the interior angles of a polygon. In this case, we have a quadrilateral. So because this is 90 degree, this is 90 degree, and this is 120, immediately you should recognize that this is also 60 degree. So how do we calculate CD based on what we have here, AB equal to 3 and BC equal to 4? So at this point, if you have a good sense about geometry, then your feeling would be, well, we have 90 degree here, we have 60 degree here. They already gave you 2 of the 3 angles of the special 30, 60, 90 angle. Then it's very natural to just based on those 2 facts, find a special 30, 60, 90 triangle. And if you just think those are 2 angles of such a triangle, then where is that triangle? So without much thought, you should think about doing auxiliary lines like this. You extend DA and extend CB. That will give you a 30, 60, 90 triangle. Let's call this point E. So triangle CDE is a special 30, 60, 90 triangle. And not just because of that, because this is also 60 degree. So we also have a smaller 30, 60, 90 triangle. Triangle ABE is also a 30, 60, 90 triangle, right? Because obviously angle CED or BEA, the same angle, we just name it differently, this is equal to 30 degree because this is 60 degree or because this is 60 degree. Either way, you can show this is 30 degree. So not just found 1, but you actually found 2 such special triangles. And you already know AB and BC's length. So based on those facts, it's not too difficult to derive what you need, CD here. For example, because CD is the shorter leg of the 30, 60, 90 triangle CDE, if you either can find the length of ED or BC, either one based on the overall 1 to the square root of 3 to 2 ratio, you should be able to calculate CD. So let's just, for example, give it a quick trial, okay, shall we? So because this is 4, BC is 4, to get EC, all you need to know is BE, right? Because CE equals to BC plus BE, and you already know BC is 4. So our goal, for example, if we want to get CE, in order from CE to get CD, then all you need is to get BE here, which is this portion. But how long is this? Immediately this is 6, because now you are looking at this smaller 30, 60, 90 triangle, and the shorter leg is 3, so the hypotenuse BE must be 6. Therefore, CE equals to 4 plus 6 equals to 10. And if CE is 10, based on this ratio, then we can easily get DC or CD, it doesn't matter which way you want to say it, CD must be, because of this ratio, be very careful. So you also need very, very solid skill on those ratios, proportions, and so on, in order not to make some silly mistakes. So this is the 1 to square root of 3 is the ratio between the shorter leg to the longer leg. Now we already know the longer leg is 10, so the shorter leg would be 1 over square root of 3, and then times 10. Of course, we can simplify this a little bit. You don't have to, but typically you are expected to do some simplification like this. So the result must be this. Okay, so this is a very actually simple problem. All you need is to recognize some special angles already given to you and to think about a way how to take advantage of that. But when you have this 60, you probably recognize that there's another way to extend this. So I'm now using the blue line and making this a little bit smaller so that we have more space. So if we, because this is 60, now we are extending this side and this side, but we can do in the other direction as well. So if we extend this way, you will pretty much get the same idea. It's just on the different side, right? Now what do we do? You get exactly the same situation. You get another 30-60 triangle, if we call this F. Then you get triangle ADF. This is also 30-60-90 triangle. And this triangle BCF is also 30-60-90 triangle. So almost the same idea, but you just do it in a different way. For example, if this is 4, then this must be 4 times square root of 3, because angle BCF is a 30-60-90 triangle. Then now you get this, you can calculate this one. This is longer, this is 8. So this is 3. So AF equals to 8 plus 3 is 11. And then you can get this one, AD, as the hypotenuse based on AF. Then finally subtracting 4 square root of 3, you get CD. So it's essentially the same procedure, it's just a different way. But the takeaway here is that for problems like this, if you have never done any auxiliary lines, you may get stuck because there's no way to immediately get what you want from what were given to you. And that's normal, because usually doing a geometry problem requires you to do some auxiliary lines. And that's the most beautiful part of geometry, because you have to think outside the box, not limiting yourself to what you immediately see on the paper, but you have to imagine there's something that has not been drawn to you yet. So that's what happened, okay? But the fundamental thing is that you want to gradually develop some intimate feeling, your gut feeling about the nature of the problem. And here is you have a lot of right angles, and you have a special angle which is 120 degree. And that allows you to find some further special triangle. All right, let's move on to the next problem. Okay, problem number 2. Oops, this is number 3. Did we? Yes, this is number 2. Okay, so what's happening here? We have a regular hexagon. Everybody should understand what is a regular hexagon, meaning that all the sides, a hexagon is a polygon that has 6 sides. And a regular hexagon is that all the sides are the same or congruent, and all the interior angles must be also congruent. And it's not difficult to see that each such angle, interior angle, should be 160 degree, because the formula for such the sum of the interior angle would be 6 minus 2 times 180 degree. That should be sum of all the 6 congruent interior angles. And because they are congruent, each one of them is this sum divided by 6. Therefore, easily this is 120 degrees. So a regular hexagon is something, each interior angle is 120 degrees. Those things you should memorize, but it's not really hard to memorize it because you understand why it's like that. So you do need to know this fact. So what is happening here? We have such a regular hexagon. Oops, well, my drawing is pretty bad for this. So we want to get a reasonably good drawing by hand, but to me that's typically a little bit challenging because I'm drawing on a touch screen. So we have certain circles that are inside this hexagon, but they are not randomly chosen because they somehow give you a very kind of unique result. That is, all the 6 circles are tangent to the sides and they are tangent to each other. Now the question is, how do we get the perimeter of the hexagon if you know the radius of the circle? All the 6 circles are congruent. So when you have a problem like this, what is your first gut feeling about the nature of the figure? Look, this looks so nice, right? Also a little bit complicated, but it's very nice in the sense that it's kind of symmetrical in many ways. For example, if you draw a diagonal line of the hexagon, you divide this figure perfectly into 2 halves. That's symmetrical about this diagonal line of the hexagon. On the other hand, if you somehow think that you can draw a perpendicular here, it must also divide the whole figure into 2 symmetrical parts. So it's also symmetrical about this line, and this line should be easily connecting the 2 midpoint of the 2 opposite sides. Not just because of that, if you think there's a center, and because this is a regular hexagon, so there's a center right there, which can be easily the intersection point of the 2 diagonals. Okay, so this has 2 opposite diagonals from here to here. So there's a center of the hexagon, and this center must also be the center for the whole figure as somehow what we call central symmetric. So if you rotate the whole figure by this point by half a circle or 180 degrees, it must be come back to itself. Okay, not just that, you can think about it. If you actually just to connect excuse me, this center to all the 6 circle centers, you must have the same symmetry right there. So this must be a smaller regular hexagon, just because of all these symmetry properties. So that really gives you the clue of how to find what you need. Okay? Another thing is that you have to understand the very nature of tangency. Typically, what do we mean by tangent? We have a circle. It can be tangent to a line, meaning that the circle and the line intersect at exactly one point. And you potentially can have a circle-to-circle tangent like this. And there are 2 types. One is the interior, one is the exterior, but fundamentally pretty much the same property that determine how they are tangent. So let's take a look at the case when a circle is tangent to a line. What is the fundamental property of such a phenomenon? That is that if you connect the center of the circle to that tangent point, you can feel that this must be perpendicular, right? Because there's no way the left-hand side and right-hand side are not symmetrical. Indeed, they're symmetrical. Therefore, both angles must be 90 degrees. You divide equally this line into 2 halves. So, yes, that's correct. Whenever you have a tangency like this, a line to circle tangents, if you connect the center of the circle and that tangent point, this radius must be perpendicular to the line. And vice versa. Whenever you have such a case, you get a tangent, if this is the only point. Okay? So, what is the circle to circle tangency? Well, because the two circles intersect at the exact one point, it can be easily shown that if you connect the two centers, it will pass this tangent point. And this can be also intuitively understand again, because otherwise we will not have this symmetry, right? So the fundamental nature is that if you connect the two centers, it must pass through that tangent point. Not just that, if we draw a line that is tangent to both circles, this line, which means that you separated the two circles with just one line. This line is unique, and it must be perpendicular to the connecting line segment connecting to two circle centers. So this is the fundamental property when you have circle to circle tangents. So for this problem, our goal is just to derive the size of this side of the regular, the biggest outside hexagon regular, a regular hexagon, right? Because we need to know the perimeter. So we just, if we know this, it times 6 will give you the perimeter. Then how do we figure out this? Well, by all this symmetrical nature, you can see that if we connect the center of this hexagon with those two vertices, what do we have? This must be an equilateral triangle. Why? Because we are essentially get 1/6 of the full circle, so this angle must be 60 degrees, right? And this is an isosceles triangle because this side congruent to this side, so this is a isosceles triangle where you have one of the angles, in this case the top angle is 60 degrees, so this must be an equilateral triangle. That's significant development because this is such a special triangle, we can see how we will get it. Now, if you look at the green, the smaller regular hexagon, you will see that this from this center, which is center of one of the 6 circles, to the big regular hexagon center, which is also the center of the smaller green regular hexagon, you will see that this is also an equilateral triangle, right? But what is the length of this side of this equilateral triangle? It's just twice of the radius of the small circle, because we just shown that when you connect this, it goes through that tangent point. So this side is just 2 copies of the radius. Okay, what is the length of that radius? It's 1. So therefore, this is 1 times 2. So this is 2. Then accordingly, this is also 2, right? Then we will see that this length, which is the altitude of the equilateral triangle of interest, will be 2 plus 1. Let's get rid of this. Because this is the radius, it's again 1, but this one is 2, so this will be 3. That means that the altitude of this blue equilateral triangle is 3. Now you know how to get the side of this equilateral triangle. This must be 3 times, be careful, you have to get on top of how the ratio works. This must be times 2 over square root of 3, because this is the ratio between the hypotenuse and the long leg of the 30, 60, 90 triangle. So therefore, this is what you get. And coincidentally, because this is 3, we can actually cross out and change this to square root of 3. So this is 2 square root of 3, and that is the length of the equilateral triangle. And then you simply multiply this by 6 to get this 12 square root of 3. So what do we learn from this problem? Is that don't get intimidated by a complicated or seemingly complicated figure. You still just want to get to the bottom of the nature of the figure. In this case, you have 6 circles, and they're all tangentially connected, and they're interior tangent to a hexagon, regular hexagon. But this is such a nice figure that gives you a lot of just a very easy to find hidden geometry figures. And you really need to have a very good sense about the nature of such figure. Symmetry, if you have 6, then you have each angle is 1/6 of the full circle, that's 60 degrees, and all those things will take time to develop. But along the way, you want to, every time you have work on such a problem, you should take a deep breath to think about the nature of this problem. So next time when you see a similar figure or problem of similar nature, you can recall what you learned. And that is how you develop your geometry sense. I believe that you develop your number sense probably along the same way. Okay? So that's what we learn from this problem. Okay. Well, 2 angles of the triangle measure 30 and 45. And if the side of the triangle opposite to 30 degrees is given, okay, let's draw it. So we draw first a 30-degree angle. Typically, if you think about 30-60, that's a basic scale for you to reasonably draw, just because it's hard to draw that angle precisely with bare hands if we don't have any tool. But if you see that this is does this look like a 30-60 triangle? Probably a little bit off. So maybe I would need to make this angle a little bit smaller. But now this looks like 30-60. But the goal is to draw a 45-degree triangle. So this will be 45 rather than 60. So hopefully it's close to what it is. So this is 45. Then you get, what is this angle? It must be 105, right? This add up to 180. So what does the problem say? It says that the side opposite to 30 degrees is 6 square root of 2. So we know this. Now, that's all we have. What is sum of the length of the other 2 remaining sides? Well, if we label it A, B, C, as we mentioned earlier, when you have something like this, you should really just deploy your geometrical sense about this. What is the nature here? We know this side, and this side happens to connect to a 45 degree. And on the other side, you have 30-degree angle. What do you want to do? You want to build something that is conveniently, just computationally easy, right? So we want to find some special triangles in this case in order to take advantage of the information that was given. So if you have 45 degree here, what do you think? Of course, I'm thinking about I want to build a 45, special right triangle. And in that case, this side, which is known 6 square root of 2, must be the hypotenuse or the side of that 45, the leg, right? If it's a leg, it must be something like this. That doesn't seem very promising because it further pushes this special 30-degree into a very kind of narrow triangle for which we don't know how to compute. But if this is the hypotenuse, then in order to find this 45-45 triangle, we must draw our auxiliary line in this direction. Bingo! Once you see this, you immediately know you have solved the problem. Why? Because when you draw a perpendicular here, you not only create a 45-45 triangle on the right-hand side, simultaneously you create a 30-60-90 triangle on the other side. Because now this is the right triangle, this is the right angle, and you have 30 degree here, then you know how to do everything, right? Because now this is on the right hand side, this is 6 square root of 2, so this must be 6, and the height must be also 6 because this is an isosceles triangle, and therefore this is 6, which is also the shorter leg of the left hand side 30-60-90 triangle. The hypotenuse must be double that, so AB is 12. And if we call this D, then BD must be 6 times square root of 3. Now we essentially solved everything. So because BD is 6 square root of 3, BC must be 6 square root of 3 plus 6. And we already know AB equals to 12. So a very easy problem. The only thing you need to do is to draw this perpendicular. It may be difficult for beginners to see this right away, but trust me, once you have done enough problems and goes through a process that I call building your geometry sense, then at the end of the day, this almost comes naturally to you, okay? It's also because in AMC Mathcounts, those relatively easy math competitions, the problems were written in a way for you to do this very easily, okay? Trust me, those are the easiest geometry problem you will do. I mean, for competition math at least. Okay, so next problem. Okay, so we have a right triangle ABC here. It's kind of long, narrow, which is fine. ABC, did I? Oh, this is a B. Maybe I did not draw it well anyway, so I will redraw it. Make sure that I got it correct. BAC, yes. BAC, there's a D here. What does the problem say? It says the shorter leg is 15 and the hypotenuse is 39. And there's a special relation BD equals to CD plus 9. Okay. So you want to find AD, which is this one. Let's just highlight it with a different color so that we know what is going on here. What is the first thing coming to your mind with some conditions like this? It may be a little bit surprising, but I will tell you what. The first thing coming to my mind at least is that I will immediately say AC equals to 36. What? Are you kidding me? How do you know? Well, because you are doing competition math, right? There are some very fundamental things you need to memorize. And one of those things is the what so-called Pythagorean triples. When you have Pythagoras theorem, those three sides have a set relationship, and there's the so-called Pythagorean triples. All the three sides, the two legs and the hypotenuse, they are all integers. For example, 3, 4, 5 is such a Pythagorean triple because 3 squared plus 4 squared equals to 5 squared. Everybody, even if you don't do competition math, you should know this and memorize this, right? And some relatively small integers, Pythagorean triples, you should really memorize just for the sake of getting advantage in a time-constrained competition math. And one of them is 5, 12, 13. Because 5 squared equals 25 plus 12 squared, that's 144. By the way, you should memorize all those perfect squares within 25. That's 144. That equals to what? 169, which is 13 squared. So that is a Pythagorean triple. And what do we have here? Well, it's very common for math competition just organizer to give you numbers that are actually very easy to work with. So when you have Pythagorean triple, one of the things that if you scaled up a Pythagorean triple by a constant a, let's just say you get a 3a, 4a, and a 5a, where a is any number. It doesn't even need to be an integer. It could be a fraction. But the point is that when you scaled up a Pythagorean triple by the same number, the relationship still hold up. And it's easy to see why, right? Because now you can factor out a square, you still get this one equals to 5 squared, a square. So because you can cancel out a square, it still boils down to the fundamental Pythagorean triple. So that means that when you have a Pythagorean triple, if you scale it up, you will still get a Pythagorean triple. So that's what happened here. 15, it's 5 times 3. 39, it's 3 times 13. 5, 13, right here. And I know this is a Pythagorean triple just by scaling up with 3. So this must be 12 times 3. 12 times 3, that's 36. So I immediately know AC is 36. All right. So what happened? Nothing happened. I just had some basic knowledge so that I don't have to go through a process like this. You can do that, but you will lose maybe 30 seconds, maybe even more, depending on how good you are at numbers. So this is really convenient. I use my number sense and geometry sense to get some result maybe in 5 seconds. Okay. Now what? Well, you want to know this AD, right? Let's just say if this AD is x, I want to know x. I have one variable. For one variable, I need at least one, actually not at least, exactly. If I don't have any other variables, I just need one equation to solve this. And where does that equation come from? It must come from some relationship. Do I have any relationship? Well, we were told that there's such a relationship that I have not explored. I want to take advantage of this. Okay, so this triangle 15, 36, 39, this right triangle has already been fixed. You cannot do anything about it. So the only thing in this problem is where is D. You have to think about this way. Can I freely choose a point on AC to be D? No, because you are constrained by this relationship. BD must be equal to CD plus 9. So if D is very extremely close to C, CD almost 0, that means that BD almost 9. That cannot be the case, because when D is extremely close to C, BD is very close to BC, which we know 39. So D cannot be too close to C. On the other hand, can D be very close to A? For the same reason, it cannot, because in this case, BA is only 15. If let's say D is here, BD is almost the same as BA. There's no way for BD is here equals to CD, which is AC, almost like AC, 36 plus 9 equal to 15. So D actually cannot be free moved. There's one point that must exactly satisfy this. The way to think about this, if we can find the point D, is this D unique? It must be unique. Why? Because if you move D toward the left, BD, which is the hypotenuse here of triangle ABD, it will go down, right? If move D downward. On the other hand, CD will go up. So this equation will be broken. And for the same reason, you cannot move that D. Once you find it, you cannot move it rightward. Because if that's the case, CD will go down, but the BD will go up. Once again, this will be broken. So you should feel confident, and this can be easily filled out. Not just a rigorous proof, you can see that there's a unique point on this AC, D, that can meet this condition. But how do we translate this relationship into an equation? Because we have both BD and CD here unknown, right? Well, if we know AD is X, that's what we want. We call that X. What is CD? CD is easily 36 minus X. Now we got CD. What is BD? Well, BD is the hypotenuse of right triangle ABD. So BD is square root of 15 squared, that's the other leg, plus X squared, which is AD. So BD is constrained by this relationship. Now we know both CD and BD in terms of X, and they have a special constraint like this, so we can easily write this equation: 15 squared plus X squared, take a square root, that's BD, is equals to 36 minus X plus 9. Whoa! That is a good equation. First, you see that this is the equation that is solvable, right? You only have one variable, and you should recognize that the right-hand side is 45 minus X, and the left-hand side is square root of something that contains a quadratic term. So if you take square of both, you can see that the quadratic term will actually disappear, because this is x squared plus 225. It's squaring the left-hand side. The right-hand side would be x squared minus 90x plus 45 squared. Don't you see that? X squared is gone. So the rest, they say, is the history. Okay, we'll move on. All right, so we have 5 minutes, so probably we need to be a little bit faster. So probably I can skip this one because it's very similar to early problem. Two angles of the triangle measure 45 and 105. Don't we
just have that triangle earlier. This is 30, this is 45, and this is 105, right? So it looks like the same triangle, which we did in problem 2 or 3. If the side of the triangle opposite the 45 is 8. Now I get it. Last time we were told opposite to 30. This time opposite to 45. But essentially the same thing, right? So what is sum of the other remaining? Yeah, LPS, you just... Actually, this is the Mathcounts. They were just lazy. They recycled the same problem. Ostensibly made it different, but essentially the same problem. We know exactly what it is. So we draw a perpendicular here, get the result. Last time, remember, we were told this is 6 square root of 3. This time, they told us this is 8. It doesn't matter. The same problem, just with different numericals. So we'll skip this problem. It's essentially similar to what we did in problem 3. All right. Okay, there's one more problem. We have a pentagon. Looks complicated. Pentagon, that means 5 sides. 5. Whenever the number goes up, it makes problem, at least on the paper, more complicated. So BC equals CD equals D equal to 2. Angle E is a right angle, and B and C and D is 135. That's a very nice number because it's the supplement of 45, right? 135, 45. So whenever you see something like this, you will feel this is not a big deal. I can do it because it looks so nice. We like that. All right, so let's try to make a good, because there's angle E here, which is 90 degree, I believe. So we start with that angle. Yeah, E is right angle. And then E, B, C, D. So B, C, D, all 135. So if we say this is D, try to make it 135. And it says that DE is known 2, right? So DC is also 2. So essentially, you just keep going, draw the same length, then draw another 135. So, if this is 135, this must be, actually, you can see that this must be parallel to the base here, because this must be 45, 45. So that's okay. DCB. Okay. Pentagon. We already have 4 sides, so this must be the other side. Okay, not perfect, but hopefully it works. So BC equals to CD equals D equals to 2, and BCD all 135. 135. 135. Okay, the length of AE is the bottom base, can be expressed in simplest radical form as A plus 2 square root of B. And what is the value of A and B, so that you can get A plus B. This looks, by the way, this looks like an AIME problem, right? If you know what I'm talking about. All right, so this is AE is 2A plus 2, A plus 2 square root of B. And this is 2. Okay. So, how do we approach this problem? Well, you have so many nice angles, 45, 45, 45. You should take advantage of that. First of all, what is this angle anyway? Well, you have 3 135, so that's 135 times 3. You have another 90 right here. If we plus this as x, you have the sum of 5 interior angles. So that has to be 5 minus 2 times 180. once again, this is the formula for summing all the interior angles. So this is 540, 3 times 180. So this is, you have to subtract that by 135 times 3, that's 405. So you have time subtracting 495. And you get 45. Not surprisingly, this is 45. All right? And how did I get those numbers relatively quick? Why I know this? Number sense. If you want to competition math, you have to develop some number sense, mental math, all that. They will all be very helpful because during the time constraint contest like a Mathcounts, you just don't have time to do basic calculations. Everything should be processed in your mind rather than on paper. Your mind will operate much faster than your hand. All right? So if you did not understand why you want to do mental math, now you should understand. Every time you save 20 seconds here, 15 seconds there, they all add up in a huge way. If you cannot develop that kind of mental math capability, guaranteed you won't do very well in the competition math like Mathcounts. All right? So this is 45. Then I should immediately say, I want to draw a huge perpendicular here because that gives me a 45 right triangle. I will deal with what that is later. So then you want to see that because of this, you also want to draw something like this. By the way, this is a parallel, right? BC is parallel to AE. This can be easily proven because this is right. This is 135 subtracting 45. This is a 90 degree. So BC is parallel to AE. So you want to draw a perpendicular here. Let's call that point F. So what do you get? You get a rectangle here. And you get a trapezoid on top. But you want to further draw another smaller rectangle. Now, with all the data you have, this is not that difficult to compute everything, right? Because now, for example, this is 2. This is also 2, because this is a 45 triangle. This side, or BF, must be square root of 2, right? Because the hypotenuse now is 2. So this is square root of 2, and this must be also square root of 2. How do you get the rest? We already know this is 2. So everything can be easily computed. Okay? So this is 2, this is 2, and this is square root of 2 because of this. How about this side? This side is just 2 plus square root of 2 as well. So this is also 2 plus square root of 2. And finally, because this side is congruent to this side, you can get this is also 2 plus square root of 2. Okay, so you add them up, find that a plus 2 times b, figure out what a is b, add it up. So this problem, it takes a lot of time to draw the figures than do the calculations, because all the numbers were intentionally designed to be very simple. Okay, it does take much time to draw the figure correctly, all right, and do something like this in your mind, not on paper. I will see you next week.